Hello and welcome to this day of Bitkom's Quantum Summit. I'm Merle Uhl, a Policy Officer for AI and Digitalization, and I will guide you through the program until lunch. We will dive deep into the technological state of the art and existing solutions in quantum computing. We'll look at opportunities and barriers that shape the pace of innovation and widespread adoption, and we'll see use cases and applications. So you know what to expect from the day. And without further ado, I'd like to introduce to you our first speaker. Dr. Roman Bansen, he's Senior Program Manager at Cyberagentur, an agency for innovations in cybersecurity. Hello, Dr. Bansen. He will answer for us the question, which qubit is best, the current state of the art in different qubit platforms. Qubits, as the basis of all quantum computing, can be physically realized in a multitude of ways using very exotic materials and particles. The talk will give you an easily understandable overview of these different platforms and their respective potentials and challenges. We are very curious to hear from you which qubit is best. Dr. Bansen, this stage is yours.
Thank you very much for the nice introduction. I'm very happy to be back here, I have to say, after initiating and organizing this summit for Bitkom last year, now being here from the other side as a speaker. I want to take a step back in my talk. Most talks in the summit this year are about applications of quantum computing, which is great, is fantastic to see how it's evolving. But I want to take a step back and show you that there are actually very different approaches on the physical level, how those qubits, how the basis of quantum computing is implemented. Before I do that, though, let me give you a short introduction in what I'm working now for. I'm working for Cyberagentur. We are financed by the German Interior Ministry and the Ministry of Defense. We have quite a bit of money to initiate and finance ambitious and risky research projects. We want to finance, we want to support disruptive innovations with long time frame, with long time scales. And the main message that you should take from this is that we are very open for ideas and suggestions, especially very out of the ordinary ideas and suggestions, which might be security relevant, obviously, for those ministries in the future. Feel free to contact me. My email address is there at the bottom. It will be shown at the end again. And let's talk about it. Maybe it's of interest to us and we would consider financing this. So to start into the talk, let's have a short look back into how normal and how classical computers actually developed. That happened in the 1940s, 50s mainly, the early developments. And in the very beginning, in those first 10, 20 years, it was still pretty much unclear what's actually the best ways to physically realize the basis of information today, the bits. So originally in the first computers that was done with relays, then it went to diodes and tubes, and eventually to transistors, which evolved further into so-called field effect transistors. And it always stayed there. To be precise, silicon-based field effect transistors. I mean, they evolved further. They got more and more miniaturized to unbelievably small levels. It's amazing what has been achieved there, but it doesn't change the fact that for the last 70 years, more than 70 years, it has all been silicon-based field effect transistors. So the question is now, what is the silicon field effect transistor of quantum computing? And the answer is, we don't know yet. Because quantum computers are basically now in where the classical computers were in the 1940s, 50s. And the possibilities to implement those qubits, those basic units, are extremely diverse. You can encode qubits in very different physical properties, like in the spin or the charge of particles, in the polarization of light. and very different properties, and you can do that in different physical systems. Most approaches use some form of elementary particles, like in electrons or photons. They do it in molecules, but even in states of light or other physical systems. And in the next layer, again, that means you can have very different approaches, very different platforms building on those different physical systems. So there's a multitude of platforms, and I will give you a short overview over the 6 most common ones in the next few slides to show you what is being researched most on. So the most common one is clearly the so-called superconducting qubits or Josephson junction qubits. I would say, I wrote here they are the currently most advanced. Actually, it's more like they are the most successful approach, most successful also in marketing, because nowadays when people think of quantum computing and want to use a picture of quantum computing, you always see those things here on the right, those nicely golden colored thingies. The basic unit, though, is this so-called Josephson junction, which is basically just 2 superconductors divided by a very thin divider, usually an insulator. And don't worry, without going into the physical details, let's say you can make a qubit, you can encode a qubit in this structure. And this structure you can put on a chip. You can put a lot of them next to each other on a chip. You can interconnect them. I didn't do that in my little picture. And then in another layer on the chip, at least that's currently the most common approach, you put other structures from which you operate those qubits, those Josephson junctions, like to entangle them, to do the readout. You do that by microwaves. And the whole stuff works quite well. Obviously, that's why it's so far advanced already. It needs very low temperatures though. So the structure on the right that I mentioned initially is actually all those different levels that you see here are basically just the different temperature levels. You go down further and further in the temperature, almost to absolute zero. And the actual chip where those qubits are on is just in the very bottom down here. So the state of the art here is that we are, depending on which company, which research groups you look at, that we're somewhere in the range of about 50 to about 150 qubits now. And I think, I mean, those are usually, or on all of those slides, they're all my personal impressions, my personal opinions. But in my opinion, it's quite reasonable to really believe those presentations from the companies that we will really reach about 1,000 qubits here within the next few years. But let's go on to the second approach, also very common, the trapped ion qubits. Some of you might remember this famous photography award winner from 4 years ago from showing a single atom, or actually a single ion, visible to the naked eye in an ion trap. So this is what those ion traps look like. And you can encode a qubit in an ion. And you can actually put more than one. You can actually put quite a number of ions in one ion trap next to each other. You can operate on them. You can change them with a laser. You can entangle them with a laser, and therefore do computation on them and with them. Now, it's still very limited to how many qubits you can put in one trap here this way, but in recent 10 years, there has been a lot of miniaturization, and you basically create those kind of chips or structures where you are able to have more complicated versions of those traps, which are able to trap much more qubits. And in newer versions and newer approaches in the last few years, you're even able to move the ions around within on those structures, on those chips. So you have like areas where you can store ions. You have areas where you operate on the ions, where you entangle them. So with this, there's possibility for scale up. One advantage of this approach is that, at least in principle, it can be used at room temperature, though usually it's used at lower temperatures. The state of the art here seems still very low. We are talking about 10 to 20 qubits max at the moment. But it has to be said that the quality of those qubits is very high. So those 10 to 20 in their performance actually compare quite well to the about 100 qubits in the superconducting approach. And in reach in the next few years, I'd say is maybe up to 100, around 100, maybe a bit optimistic, but then again, they are quite high quality qubits. Let's go to number 3. That's the neutral atom qubits. I always find it a bit confusing that they are called neutral atom qubits, because to me, atoms are usually neutral, otherwise they would be called ions. What you do here is you encode the qubits in special states of the electrons around those atoms. And what you do with the atoms, the special thing here is you trap them in a so-called optical lattice. And to understand this very easily, if you shine two waves of light over each other, you have exactly in the same way as with those water waves in the picture on the right, you have interference, you have ups and lows, you have hills and valleys. And in those valleys, you can trap the atoms. So in 3D, that looks like something like this then. And that works surprisingly well. And then again, you can use, for example, a laser to operate on those atoms to encode your qubits there, to entangle them and do calculations with them. You need extremely low temperatures for this to work properly, but there have been quite some interesting successes here in recent years. The state of the art here is very diverse, depending on which groups you look at again. That's why I put such a large range. So somewhere between 10 and around 200 qubits, I'd say, is realistic for the current state of the art. And it seems quite realistic to really assume within the next few years to already achieve 1,000 qubits here. More than 1,000 atoms in this lattice has already been shown. That is actually doable quite well. Of course, that doesn't make them usable, controllable qubits yet. Number 4 in our little presentation here is photonic qubits, and those are actually the most weird ones or most different from the others. So you use light here, you encode the qubits, which in this case work so differently that they are usually referred to as Q modes and not as qubits in states of light. Using light has a lot of advantages, but it has a big disadvantage. Light consists of photons, and photons don't like to interact with each other. So to overcome this problem, you have to use, let's say, more interesting, more out of the ordinary approaches. You have to use some tricks, not going into details here. But let's say the whole computation process where you do the actual computation is very different from the other approaches. You use a lot of mirrors, beam splitters, phase shifters for the light to do the actual computation, basically. And traditionally, you did do this on those large optical tables. But in recent years, this is getting all miniaturized and integrated onto chips. Even the photon sources and detectors are being slowly integrated on the chips. The goal is to have everything on one small chip, and this really gives a lot of potential for upscaling, and therefore for making this actually a very successful approach in the future. One advantage also is if you use light, it can be combined with other light-based quantum technologies, like, for example, quantum communication. You wouldn't have to convert your information from quantum communication. You can theoretically at least directly use it in quantum computation and combine the two. Also, it's an approach which, again, at least in principle, works also at room temperature, although it's usually in all those approaches gives better results if they are cooled. The current state of the art is somewhere between 5 and 20 qubits or Q modes. And I find it very difficult to put a number here to what's in reach in the next few years. So I put this vague range of 100 to 1,000 qubits. I think there's really a lot of potential here for upscaling. If you believe companies like PsiQuantum, then we're at 1 million qubits in no time. But so I'd say somewhere in that range is realistic. Number 5 out of 6 is NV center qubits, also called diamond-based quantum computing. They are really based on real diamonds. to be precise, on diamonds with a slight coloring. Especially red color here is of interest. And to be even more precise, they are artificially made diamonds. That's what they look like, the artificially made ones. You can change them in a way that you want here, and you encode the qubits in those so-called color centers, the NV centers. The N actually just stands for a nitrogen atom, which replaces a carbon atom. The V stands for a missing carbon atom next to it. So there's a vacancy. That's where the NV comes from. It's not so difficult once you understand that. It's a nice approach. One NV center isn't necessarily just one qubit, because you can have also the electrons around it as qubits. So you can have multiple qubits in one NV centers. The challenge is really to entangle the qubits of different NV centers with each other here. I think, to my knowledge, the current maximum here is 3 NV centers being coupled. Also, it's notable that you're actually not really limited to either the NV or the diamond, which is the name-giving things here, because, for example, you can use germanium or silicon instead of nitrogen, and you don't have to use diamond. You can also use, for example, silicon carbide, and then you have a germanium vacancy in silicon carbide instead. This is being researched on as well, belongs in the same category. It's another approach which can, in principle, be used at room temperature quite well. Also, it can be made very compact compared to other approaches. The state of the art here, depending a bit on the temperature level, is somewhere between 4 and 30 qubits at the moment. I'd say in reach in the next few years is still lower numbers, still maybe only around 50 qubits. That doesn't mean I don't see a lot of potential here. I just think to overcome those challenges with the different NV centers, it takes a bit more time, but there is a lot of potential in this approach as well. Last but not least, the solid state or semiconductor qubits. Of course, to be fair, the NV centers in diamond are also both solid state and semiconductors. But what I mean here is really approaches that are based on the established semiconductor industry, the big silicon-based industry that all our microelectronics, our mobile phones, computers are made of today. What you do here is you use the nuclear spin or the electron spin of things that you introduce, and the most common, or maybe not most common, but most famous approach, and maybe the oldest one, there's a lot of different approaches again, is probably the Kane quantum computer, where you introduce phosphorus atoms in your silicon. And then the nuclear spin of the phosphorus atoms is your qubits, basically. Alternatively, for example, one of the many other approaches is that, for example, you create quantum wells in a silicon layer, and then you have the electrons in there and use their electron spin as the qubits. Now, the big advantage here is, of course, that at least potentially you can integrate this entire approach with the existing huge scale electronics industry. If this is successful, then this, of course, gives a huge advantage, because this industry exists for decades and is already able to produce huge numbers of processors in very short time scales. It's another approach that uses low temperatures, though not as low as, for example, the superconducting qubits. We're still talking at the state of the art about less than 10 qubits here, to my knowledge at least. But I'd say there's a lot of potential here for upscaling, and it will take some more time. I say in the next few years we might reach maybe 50 or 100 qubits here already. But again, there's a lot of potential for the future. Now, this brings us to the initial question: which qubit is the best? Well, first, I want you to understand that there's dozens of other approaches than the 6 that I've shown you. It's just that those 6 are the most far advanced at the moment. But there's, for example, Bose-Einstein condensate qubits. There's fullerene-based qubits. There's liquid-state nuclear magnetic resonance qubits. You don't have to understand all the details here. It's not important for the message. There's topological qubits, and they are all being researched on, and they are all promising in their own way. And currently, there simply is no best approach. No one knows which platform will win. They all have pros and cons. And I also want you to understand that it's quite possible that even if, let's say, the superconducting qubits now scale up to 1,000 or even 10,000 qubits, it's quite possible that in a few years they will simply be overtaken by one of the other approaches. Let me give you a very silly example. In the 1870s, 1880s, this is what people believed bicycles looks like. Everyone thought of bicycles, they thought of this thing. And 10 years later in the 1890s, this is what bicycles looked like everywhere. No one's using those penny farthings on the left side anymore. I know not the best comparison maybe, but a funny one. And the same might happen for the qubit platforms. And also it's quite possible that eventually here multiple different platforms will permanently coexist, because for different applications, different platforms actually have their own advantages. So in contrast to the classical computers, for quantum computers, it's from current perspective actually quite possible that you really have different platforms in the future coexisting together. My last few words for this presentation. Last few words, counting qubits isn't everything. Coherence, fidelity is super important. I know that. The only reason I've done it is for the same reason as everyone else is doing it. It's so easy and you have a nice metric. You can show this many or that many qubits. In the end, it will only be relevant how the systems perform in real life applications. You only can test that with real life applications, which is why it's so great that we see so many presentations about real life applications of quantum computing in this quantum summit. And also it would be helpful to have better, proper benchmarks. A lot of them are under development, but they are not there yet, in my opinion. With that, I'm finished. Thank you very much. I was hopefully able to give you a few insights here. I'm happy if you contact me, and I'm also open for questions. I think not in the time left. There is no time left, but maybe afterwards.
Unfortunately, no time left for questions, but as you said, please reach out to Roman. I think he's happy to discuss which qubit is best and all other questions regarding the topic.